Hi, this video arose from my previous video about proving that a logarithm was irrational. So it says, prove that an even number raised to an integer power is always even, and that an odd number raised to an integer power is always odd. And we'll talk about positive integers here. Okay, so the first part is to prove that an even number raised to an integer power is always even. Okay, so if we consider a to some power where a is an integer number and m is an integer, and m is sort of a positive integer, therefore we can write a to the m, as it's an even number, the normal notation for an even number is 2k, so we can say this is 2k to the m, and then using, where k is also an integer, and then we can say that's 2 to the m, k to the m, using the fact that ab to the m is a to the m, b to the m. If we factorise out a 2 from here, we're going to get a 2, and that now means this power is 1 less, so this will be 2 to the m minus 1, k to the m. So this is 2 times 2 to the m minus 1, k to the m. These are or both integers, so it's like 2 times an integer, so we're back to like this format here. We can therefore say that this is an even number. To prove an odd number raised to an integer power is always odd is a little bit more challenging, but not impossible. So we're going to consider that a to the n, where a is an odd number and n is an integer. So a to the m is equal to 2k plus 1 to the n. This is the format for an odd number where k is also an integer. So we're going to expand this now using the binomial theorem, this bit here. So that will be 2k to the plus 1 to the n will be 2k all to the n plus n 2k to the n minus 1 times 1. This is nc1, which is always n. And then the next term will be nc2, 2k to the n minus 2 times 1 squared. And then so on. The general term will be ncr, 2k to the n minus r times 1 to the r, plus ncn minus 1. This is the last but one term, 2k, and this will be 1 to the n minus 1. And then at the end we'll have plus 1 to the n. So this is the binomial expansion of that. So let's just write that down again. We'll just jump to that. So writing that all again. Okay, so we're now going to take out a 2 from each term if possible, but the last term. So if we take a 2 out here, the same idea as before, we get 2 to the n minus 1 k to the n plus 2n, 2 to the n minus 2 k to the n minus 1, plus 2nc2, 2 to the n minus 3, 2 k to the n minus 2. And the same with the general term, we can take out a 2, so it will be ncr, 2 to the n minus r minus another 1, k to the n minus 1. And the last but one term, we can take a 2 out, so it will be ncn minus 1 to the k. So we've taken all the 2's out, now we've just got a k. And the last term we can't take a 2 out, so we'll just leave it as plus 1. And then we've also ignored all these 1 to the r, 1 to the n minus 1, because they're always going to be 1, but we do need to include the last term here. Right, we can now see we have a common factor of 2, so we can take that out. And then if we do that, we're just going to have 2n minus 1 kn, n2 to the n minus 2, k to the n minus 1, mc2, 2 to the n minus 3, k to the n minus 2, ncr, 2 to the n minus 1, r minus 1, k to the n minus r, and then so on to the last term, ncn minus 1, k, close the bracket, and we've still got the plus 1. So here we've got the same format as an odd number, 2 times some constant here, plus 1, or is going to be a odd number. We can say this is 2a plus 1, where a represents all this. This is the same format as an odd number, and therefore we just proved that the result is an odd number. Okay, this has been a video on a proof. I hope you've understood it. Please check the link in the notes of this video, because you will find access to my website where there are thousands of videos to help you with A-level maths and IGCSE maths. Maybe you could consider subscribing to my channel. Thank you very much for watching.